Hello and welcome back to California Geology. Today I want to talk about sediment maturity and turbidites. Now, maturity of a sediment describes the history of the material as sediment in the environment. History of sediment in the environment. If it has a longer history, it's going to be more mature. If it has a shorter history, it's going to be something called immature. And so there's two ways of looking at maturity of sediment. Again, remember the history of the sediment will give us ideas as to past environments and even tectonic settings. So the two ways to look at it is there's textural maturity, which deals with the size of the minerals or mineral grains, how well sorted they are, how rounded or angular they could be. Whereas compositional maturity describes what minerals could be present, and this one's really affected by chemical weathering processes. So let's first look at the textural maturity. So this one, the first one we talk about is sorting, and sorting deals with sort of the winnowing of sediment. As material moves down a river valley, the coarser material tends not to be moved as far as finer material. So the river acts as an agent working to separate the sediment. So a sediment that is better sorted would be mature or more mature over here. This is more mature. Whereas a sediment that has mixed sizes will be immature. In other words, it's still probably close to the headwaters up in the mountains still. Eventually, as that sediment travels down the valley and toward the ocean, you'll get something that's more mature. The other way to look at textural maturity is the sharp edges. If the sediment still has sharp edges, well, then it hasn't traveled very far. But if the sediment tends to have rounded, like a conglomerate, then it's traveled some distance. So this would be more mature as well over here, because the sharp edges have been abraded away by tumbling down a river valley, whereas this one over here is immature. So that's a couple of things we look at just in terms of textural maturity. Now for composition, here we look at the chemical weathering process. Remember, chemical weathering, there's either the hydrolysis, which is basically releasing hydrogen ions. And remember, the definition of an acid is something that releases hydrogen. So basically hydrogen ions, that's acid. So acid leaching of feldspars. The feldspars, like particularly potassium feldspar, these get converted to clay minerals. Clay minerals. And those minerals include kaolinite. Kaolinite is an important mineral for pottery. It's one of the main minerals used in making pottery. So feldspars, if your sediment still has feldspar, then it's not that mature. It's relatively immature because of the presence of feldspars. If your sample does not have feldspars, then it depends if it has any of these guys over here. It may be mature because it takes time to get rid of these feldspars by acid leaching. Now, the other type of weathering is this oxidation, and oxidation involves rusting, right? So that's another, oxidation is just a fancy way of saying rust, right? So anything with iron and magnesium. So the mafic minerals tend to rust. Olivine, pyroxene, amphiboles, hornblends, they tend to oxidize pretty quickly in the environment. So if your sediment has dark mafic minerals in it, then it's immature, very immature. The only mineral that's not affected by chemical weathering is quartz. Here I call it the sole survivor. Sometimes I call it the omega mineral because omega is the last letter of the Greek alphabet, so it's a sole survivor. So thinking about that, feldspars and mafic minerals, their presence would indicate that the sediment is not that mature. Now, in terms of plate tectonics, if your sediment only has quartz sand, or you get quartz sandstones, then those are mature Compositional mature sediments occur at passive margins. If you've ever been to a beach in Florida or the Carolinas, the beach is white. It's quartz sand, whereas beaches here in California are more beige or tan color because there's other minerals mixed in with the quartz. So passive margins would have the mature sediment, whereas this other sandstone, Arcos, remember this one has K feldspar. Remember this one. This has a K feldspar, and these potassium feldspars would indicate that there must be some granite nearby, some highland. So these are relatively immature because they're being eroded from this nearby highland. So it's probably, it could be an active margin, certainly a continental region where there's high mountains, which would indicate it's probably near an active margin. So Arcos sandstones are typically active margins instead of passive margins. Now, immature still have feldspar, exactly. So now for the last one, it's called a lithic or wacky sandstone. Sometimes we use the word gray wacky because there's some dark minerals mixed in. So this one would have some mafics. And then remember, the word lithic here just means stone. So usually geologists, if it's a little stone or a little piece of rock that's sand size, it's in the sediment, and you really can't identify it, you call it a lithic. It makes it easy that way. But lithic sandstones tend to occur at active margins. They're going to be immature. So we can use sandstone petrology to say something about plate tectonics. All right, well, in terms of turbidites, so turbidites are important in that they really form in one specific region. They're going to form in a place called the slope and the rise. And what happens is runoff from land, when it rains, muddy waters come down here, the gravel ends up in the river valleys, sand on the beach and in the inner shelf, and then silt out here in the outer shelf. Then you'll go off this shelf break, this drop off, and what'll happen, you have pretty even flow here, but then you'll have this very turbulent flow that comes cascading down here, and we call this a turbidity current. Turbidity current. And this turbidity current is bringing a lot of sediment. It's heavy with sediment, and it's depositing these sediments in the slope and rise region. So each bed, so note that I have several beds here in the turbidite. Each bed is a separate turbidity current event. Is a separate event. And probably a separate storm, right? And so, but the unique thing about it, these beds are graded. They go from coarser particles on the bottom to finer on the top. Coarse to fine, coarse to fine. And that's what would happen like in an avalanche. The big particles come tumbling down, and then the dust settles on top. In this case, these will be more like a fine sand, almost a silt, and this would be a silt to clay. And so they're relatively fine grained, a fine sand to a silt clay at the top. But you definitely see that graded bedding. And then the only thing that makes it out to the deep ocean in terms of this terrigenous sediment is clay. In fact, I wanted to define terrigenous sediment as well. Terrigenous sediment is land-derived, deposited in ocean. And so the shale that may form out here, the turbidite, the abyssal clay, those are termed terrigenous sediment. So let's stop here and we'll start with metamorphic.